Today we are going to talk about complex numbers as vectors. Reminder that our complex numbers, aka I, is the imaginary unit for the square root of 1. So we would say that the negative square roots normally don't give us an answer unless it is imaginary. And remember, I squared is back equaling -1 times -1 back equal to 1. So just some little reminders of imaginaries. Now, when we go to graph complex numbers, your x-axis is representing the real part each time. So any of the real components from your form a plus bi, aka the a part, and then the vertical is going to be our imaginary part that's representing the b part. So our complex number in the vector format is going to equal z is going to equal a plus bi, and you're essentially plotting a and b on there. We can also represent them starting at the origin and a and b, basically like we have done with our vectors, thinking about in standard form. So if we're going to graph each vector, vector z, if it is 3 plus 4i, we are going to go to the right 3 on the real axis, up 4 then on the imaginary part, and we would have vector z graphed versus vector v, which is going to the left 8 on the real component, up 2. So again, draw in so that we show starting at the origin, going to that vector. Here then is vector v. On the next page, then, we talk about the absolute value and the argument. The absolute value, or sometimes you'll see this called the modulus, is basically the magnitude, aka the length, if you want to think of it that way, of our vector, of our complex vector. And again, is denoted similar to magnitude with an absolute value symbol. And again, to show that distance from the origin to that point, you're essentially using your Pythagorean theorem. So again, think about the way that we calculated the magnitude of a vector, very similar in that regard. The argument, again, is like the direction. This is going to be showing kind of which direction our vector is pointing on the imaginary plane. Remember, positive is counterclockwise in this case. And again, we are going to be using tan inverse to help us calculate that b over a. Always be aware, though, of course, what quadrant you are in and if the complex number is telling you that correct angle. So for our absolute values each time, okay, again, you are just taking the square root of your a component plus your b component. In this case, 3 squared plus 4 squared is 25, which is just going to result in 5. And then our argument, okay, we are going to take tan inverse of our b component divided by our a component. So tan inverse of b over a, we end up with 53.1. Now, if you think about this graph, though, if you're going to the right 3 and up 4, you are pointing towards essentially quadrant 1 for this graph. So 53.1 does make sense as our argument because that is a quadrant 1 value, so we're good to go. For our second example, vector v is going to the left and down. So again, left and up, excuse me. So as we graphed on the last one, this is going to be kind of an upward facing quadrant 2 value. So to find the absolute value, okay, we are going to take the square root of 8 squared plus 2 squared. So 64 plus 4 is 68, which, if we're looking for the exact answer, can be broken down. Square root 4 is 2, and then square root 7. Or again, you could always have, 17. You could also have the rounded answer potentially on this, depending on the problem. Square root of 68 is 8.2 is another option if you are rounding to the nearest tenth. This time, if we take tan inverse of our b value divided by our a value, tan inverse of 2 divided by -8 ends up being -14 degrees, which is not officially a quadrant 2 pointing direction. So again, we want to be careful to make sure that our vector's direction makes sense. We can do 180 minus that reference angle to figure out our quadrant 2 equivalent value. of 166. Last but not least, we also want to talk a little bit about being able to graph the addition of these. So if we think about calculating the sum of our first vector plus our second vector given, you're going to add up your horizontal components, your A components, that's 3. Add up our B components, 2i minus 1i would just give us 1i. So our resulting sum for this vector would be going to the right 3 and up 1 as our vector to graph. So when we are looking for the absolute value of this, we would again take those A and B values. 3 squared plus 1 squared gives us the square root of 10 as the absolute value. And then for our argument, we'd take tan inverse of 1 over 3. Again, this is quadrant 1, in case we forget. So the good news is the resulting value we get from the calculator of 18.4 degrees. That is a quadrant 1 value. So that would be our resulting argument. All right, thanks everyone for watching. We'll work more with these in class.